Welcome to the Solutions to the Regents Physics Static Electricity Problem Set, problems numbers 1 through 4. Number 1, how does the charge of an electron differ from the charge of a proton? Well, as you may recall from chemistry, and you even had this in middle school, perhaps elementary school, that an electron has a negative charge and a proton has a positive charge. We also know that they electrically neutralize each other, so that the charge of the electron must be the same in magnitude but opposite in side. So a charge of an electron is negative 1.60 times 10 to the negative 19 coulombs, while the charge of the proton also is 1.60 times 10 to the negative 19 coulombs, but it has a positive charge. Number 2, using a charged rod and an electroscope, how can you find out whether or not an object is a conductor? You've done a little bit of work with the electroscope already. That'll make it easier to understand this diagram. So in my diagram, here's the electroscope, and in its neutral state, each of these positive charges would have a negative charge associated with it. And here are your two leaves in its neutral state, again, each with a positive and negative charge. Here's your unknown object that you're trying to figure out whether or not it's a conductor. And you would attach this to the side of the knob of your electroscope. Okay, so you would attach it to the side like over here. Then you would bring a charged rod near it. We'll let this one, just for example's sake, be negative. And you know that this object right here is a conductor if the leaves diverge. How would you know that? Well, bringing the negative near here, if this is a conductor, would cause the negatives to move away and down into the leaves. This would make the leaves more negatively charged on both sides, and negative repels negative. If you bring this charged negative rod near this object and nothing happens, then you know that this object is an insulator. It does not conduct electricity. Electrons won't move easily in it. So that's how you can use the electroscope to find out whether or not an object is a conductor. Number 3, explain what happens to leaves of a positively charged electroscope when rods from the following charges are nearby but not touching the electroscope. In other words, brought close enough so the spark doesn't jump between the two. All right, so here we have a positively charged electroscope, and positively charged meaning we would show no electrons at all in the leaves. So I know this is showing it diverged with electrons down here. Your initial diagram would start out with 4 positive charges in the knob and 2 positive charges in each leaf, and that's it. Okay, now what happens when we bring a positive rod, as an A here, near but not touching the positive knob? This will attract electrons that are still in the leaf, though we didn't draw in the diagram. So here's the trick. Just because we say it's positively charged doesn't mean there's no electrons in it. It just means there's more positive charges than negative charges. In other words, there's an absence of electrons in the electroscope that is positively charged. Okay? It doesn't mean there's no electrons here. It just means there's an absence, generally speaking, overall, of electrons. Well, these electrons that are here are going to get drawn up into the knob up here because of this positive charge. They will be attracted to this positive. What does that do? If electrons move from the leaves up into the knob, it makes the leaves even more positively charged. So the leaves started out as diverged, and they will diverge even further. Okay, so that's the answer to A. And B, we're showing, we start off with a net positive charge here. and we're going to bring a negative rod near it. Well, what would that do? It would push down any negatives that are in the knob down in the leaves. Even though it's positively charged, again, there's still negatives in here. Okay? And that would cause some of these negatives to neutralize some of the positives in the leaf, in each leaf, making it still positively charged, but less positively charged. And so the solid line here shows how the leaves would start out as diverged, and the dashed lines show that they would be diverged less. Okay, so those are your answers to A and B of number 3. For number 4, Coulomb's law and Newton's law of universal gravitation appear to be similar. In what ways are the electric and gravitational forces similar, and how are they different? Let's start out with two objects of mass m and have a positive charge we'll just call positive Q. Okay, so you see them both positively charged. Didn't draw it here, but we'll say that they both have mass m, and they are 1 meter apart from each other. Okay. Earlier this year, you learned that the gravitational force of attraction, Newton's universal law of gravitation, Fg equals big G m1 m2 over r squared. Coulomb's law would say that the electrostatic force, Fe, equals k q1 q2 over r squared. So certainly here we see some similarities. Both are what are called inverse square laws, and that's because they're both inversely proportional to the square of the distance between the centers of the objects. So this they have directly in common. Okay? Both also have a constant, in gravitational case big G, in electrostatic case little k. And both have a product, in this case gravitational is product of the masses, and electrostatic force product of the charges. Okay, so this is the way in which they're similar. However, that is where the similarities end. If we take and substitute in, okay, and I can see what's been done here is that we've given each of these, each is a proton. Okay, so each of these charges up here is a proton. We just use powers of 10 here. The power of 10, the order of magnitude for big G, would be 10 to the negative 10. I believe the actual number is 6.67 times 10 to the negative 11. That's greater than 5.5. So you'd round up, but negative exponent, that means the negative exponent itself decreases. So 10 to the negative 10 would be the order of magnitude for big G. The mass of a proton is 1.67 times 10 to the negative 27. So its order of magnitude would be 10 to the negative 27. So m1, m2 over r squared, and our distance between centers is 1 meter. You go ahead and do that. We add the exponents together. This would be 54. 27 and 27 is 54, and 10 is 64. So the force due to the gravitational attraction between these two would be 10 to the negative 64 newtons. Let's take a look at electrostatic force. The electrostatic constant is 8.99 times 10 to the 9th. For order of magnitude, it would round up to 10 to the 10th. The charge of a proton, right off your reference table, 1.60 times 10 to the negative 19 coulombs. Well, that would be an order of magnitude of 10 to the negative 19. So substituting these in, we've got k q1 q2 over r squared. Adding the exponents together, 19 and 19 would be 38. That's a negative 38. Plus a positive 10 would be a negative 28. So 10 to the negative 28 newtons. Take a look at the comparison. 10 to the negative 64, 10 to the negative 28. While both of these forces are small, no one will argue that. The force of electrostatic, in this case repulsion, between these two protons is much, much, much greater. What is that? 10 to the 36? 10 to the 36 times greater than it is for the gravitational force of attraction between them. So electrostatic force, a much stronger force than gravitational force. All right, that'll do it for our solutions on 1 through 4. More to come with our introductory set of problems here when we do problems 5 and 6 together in class tomorrow.